In this video, we're going to finish our discussion of interference and diffraction. We'll start out by talking about diffraction, which we haven't really talked about yet, and then we're going to look at how diffraction and interference are often both present in a problem. At the beginning of our last video, I told you that you get interference anytime that light goes through two or more slits. And in the last video, we concentrated at looking at double slit interference, so light going through two narrow openings. I also told you at the beginning of the last video that we get diffraction anytime light goes through one or more slits. And so you'll notice that when we're looking at a two-slit interference pattern, there's also diffraction present, and that's what we're going to get into in the second part of this video. So what is diffraction? Diffraction is the spreading or bending of waves around edges. And the classic example of this is looking at light going through a narrow opening. You may have actually seen this before with water waves. If you're ever by the ocean and you see a small gap and you notice how the water kind of spreads out through the gap, that's what we're talking about. So diffraction is that spreading of the wave through a narrow opening. And so our light is coming in like this. Most of the light isn't getting through that narrow opening, but the light that does get through is spreading out in all directions. Now it turns out that when we actually do this experimentally, what we find is that we definitely get that wide central peak, but we actually get some other definition there as well. And so it turns out that most of the light ends up in this bright central peak. So this photo right here is of a laser being shined through a single narrow opening. So most of that light ends up in that central peak. But then we also get areas where no light comes to, as well as slightly brighter areas. For diffraction, we only have one formula, and that formula for diffraction allows us to find where those points of no light are, where the minima are in the pattern. Notice that this pattern looks very similar to, or I should say the formula looks very similar to one of the interference formulas, but it's quite different for some important reasons. First of all, we're only talking about a single slit, so the idea of D doesn't make any sense. Here we have A, where A represents the width of the slit. Also, notice that the numbering is different. Our numbering here for M does not start with 0. So the first minimum is M equals 1. Remember, in the interference formula, the first minimum is M equals 0. Let's look at an example problem. Light of a wavelength of 630 nanometers passes through a single slit of 0.015 millimeters wide. What is the angle of the second minimum? So let me draw our picture here. So we now just have a single slit. It has a width A. We're putting the light through that narrow opening and then looking at the pattern that we get on the screen. So unlike interference, where we get a bunch of little dots that all have the same size, when we have diffraction, we get that one central bright spot and then much dimmer dots going out on either side. And again, the reason we get dots here is because instead of lines, is because we're illuminating it just with a focused laser beam. Okay, so this problem is asking us to find the angle to the second minimum. So that would be right here. Remember that the second minimum here would be M equals 2. The first minimum would be M equals 1. And again, we can look at either side. It's the same. So whether we're talking about that angle theta or that angle theta, that's what's going to be given by the formula. And therefore, in this case, we'd start with A sine theta is equal to M lambda. Solving that for theta, I guess I got to get a theta in there if we're going to solve for it. A sine theta equals m lambda. Theta is going to be the inverse sine of m lambda over A. Once again, we want our calculator to be in degree mode because we want our answer in degrees. And also notice that we have to make sure that lambda and A are both in the same units, because when we take the inverse sine, it's got to be of a dimensionless quantity. So to plug in then, I've got the inverse sine of m lambda over A. So m is 2 in this example. Lambda is 630 times 10 to the negative 9th. That will be meters since it's nanometers. Divide that by the slit width, 0.015 times 10 to the negative 3rd, since originally it was in millimeters. And if you calculate that, you should get an angle of 4.8 degrees. So that's how we find the angle to a minimum. And obviously we can ask some of the same types of questions we asked with interference. I could ask you, what's the distance to that minimum on the screen? But again, that's just trigonometry. So now that we know that we get diffraction anytime we have one or more slits, and we know we get interference anytime we have two or more slits, let's look more carefully at what we really see when we put light through two openings. So if we put light just through a single opening, this would be the intensity pattern. And again, all that's representing is what we would see if we put the laser through, which is we get this bright, large central spot, and then we get much dimmer spots going out on either side of that. And again, what the formula allows us to figure out is where these minima are, right? That's what the diffraction formula allows us to figure out. Okay, so we know that that's what we would get if we put our laser through a single opening. We've said previously that if we put our laser through two slits, then we get the interference pattern. And again, this is what the intensity pattern would look like. That's just representing that we get a bunch of little bright dots that are pretty equal in their brightness. Okay, and I'm not going to draw them all in there, but you get the idea. So what we want to think about is what happens when we really look at this. Well, we get the diffraction pattern and the interference pattern together. And what that means effectively is the diffraction pattern overall controls which area is the brightest in the pattern and specifies areas where no light can get through at all. So in other words, if I now imagine what really happens when we put light through two slits, I get the combination of these two patterns. And so here it is schematically. I've taken the interference pattern and I've put the diffraction pattern on top of it. We call that the diffraction envelope. And so the overall brightness of the pattern is controlled by that. But then within that, we actually get the little dots of the interference pattern. And so this is what we actually see when we put a laser through two narrow openings. Notice that right here and here and here and here, that's where it's dark because of the diffraction pattern. But then within that, all the little dots are the interference pattern. So if I just took the same laser and I put it through a single slit, in other words, what I would get is I would get that bright pattern, that bright central spot, then another dimmer spot here, another dimmer spot here. And so you'll notice that when I have two slits, instead of getting that, I now see the interference pattern inside the diffraction pattern. Okay, so this would just be what we'd see from a single slit. And that's what we actually see when we do the experiment. So you never actually just see interference, because if you've got at least one opening, you have diffraction. If you have 2 or more, you, in addition to diffraction, have interference. Let's look at the following problem. In a double slit experiment, the width of each slit is 0.040 millimeters, and the distance between the slits is 0.250 millimeters. How many interference fringes, or interference bright spots, will be visible in the central diffraction peak? So first of all, let's just make sure you understand what I'm asking. This, by the way, is not an accurate picture for the numbers that I've given, but let me just kind of use it to show you what I'm asking. Notice that if this were the pattern, we would definitely see the little bright spot there and there and there and there and there and maybe there, and the same thing on that side. And then there would be darkness. So the number of spots within that central diffraction peak would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there would be 11. Now again, that picture is not accurate for this problem, but that's the idea of what we're trying to do. So to think out this problem, we have to first identify everything correctly. We know that A represents the slit width, and so in this problem the slit width is 0.040 millimeters. The slit separation is what we mean by D, and that's 0.250 millimeters. And then we want to think about what are the 2 formulas we need. Well, we definitely need the diffraction formula, and there's only one of those. A sine theta equals m lambda. But then we also need constructive interference, because that's the little bright dots is constructive interference in the interference formula. In other words, the one that's d sine theta is equal to m lambda. So those are the 2 formulas that we need. Now, if you think about how to solve this problem, really what we want to find is we want to find the angle at which the diffraction pattern goes to 0, and then use that angle to figure out how many little dots of the interference pattern are within that angle. So what I'm going to do is I'm going to say I want the first minimum in the diffraction formula. So A sine theta equals m lambda, and what we're saying there is we want m equals 1. So I just get that that angle, sine theta, is equal to lambda over A. Now you may have noticed I didn't give you the wavelength in this problem, so I can't directly solve for theta. However, what I can do is I can now plug lambda over A in for theta in my other equation. So in other words, for the interference pattern, I know d sine theta equals m lambda over d, or sorry, d sine theta equals m lambda, or sine theta equals m lambda over d. And what I want to do is I want to figure out how many bright spots do I get within the angle of the diffraction pattern. So I'm simply going to replace sine theta with lambda over A. So I get lambda over A is equal to m lambda over d. You'll notice that this is why I didn't have to give you the wavelength, because it cancels out. And what I get is m is equal to d over A. Now if we figure that out numerically, we get 0.250 divided by 0.040. Notice both of those are in millimeters, so I don't need to convert. And what I get for my answer is 6.25. So now I've got to correctly interpret that. What I found is that I got 6 dots to the right of the central maximum, so 1, 2, 3, 4, 5, 6, but I didn't get to 7. So in other words, that 0.25 doesn't mean anything because I've got to get an integral number of m. And so what I found is that I got 1, 2, 3, 4, 5, 6 dots to the right-hand side. But then, of course, I also got 1, 2, 3, 4, 5, 6 to the other side. And then the common mistake in this problem is to forget the 0th order, the center dot. So I get 6 plus 1, and so my answer is 13. So we would have 13 bright interference dots within that central diffraction peak. Let's look at the following question. We've never come close to getting out of our own solar system, yet we believe we know what different stars are made of, even if they're millions of light years away. How do we know? This is a really fascinating thing. We claim to know the composition of the universe. We claim to know what stars are made of. How do we know that? Because obviously we have no direct information. We can't go and visit some distant star. Well, it turns out that we need a device that allows us to easily measure the wavelengths present in light coming from a distant object. And that device is called a spectrometer. What we do is connect that spectrometer to a telescope, and then we look at the wavelengths that are present in the light coming from a distant star, and we compare that with the line spectra of atoms in the lab. And I'll talk more about what we mean by line spectra here in just a minute. But let's talk about what a spectrometer is. Here's a simple picture of a spectrometer. So we've got some light source here, and again, that could actually be many millions of light years away, and that light could be coming through a telescope. But the idea is that we take light and we shine it on what's called a diffraction grating. Now, actually in a spectrometer, this could either be a prism or a diffraction grating. But we're going to talk about a diffraction grating because that's what you would actually see in a research grade instrument. We know that what a prism will do is it will take white light and spread it out into its different colors. Remember, that's called dispersion. And so we could use a prism here, but instead we use a diffraction grating, and that's what we want to talk about. What is a diffraction grating? So a diffraction grating is basically just the double slit, but with many additional slits. So it's a large number of equally spaced parallel slits. And I mentioned it should really be called an interference grating because really it's an interference pattern that we get from it. You'll notice that the path length difference between adjacent slits is just the same as it was for the double slit, d sine theta. And so it turns out when we put light through a diffraction grating, the formula to find where the maxima would be on a distant screen, or on a screen, is exactly the same formula as just for two slits, because mathematically it works exactly the same. So d here now represents the distance between adjacent slits. So let's talk about what a diffraction grating actually is or how it's made. Usually what's done is a bunch of lines effectively are drawn on a transparent piece of material, and then that is miniaturized down in a photographic kind of process. So what the lines do is they block the light, and the space between the lines is actually how the light gets through. So that's how we produce a whole number of little openings right next to each other with an equal amount of spacing. In general, for a diffraction grating then, what we're given is not the distance between adjacent openings. We're simply given the number of lines per distance, like the number of lines per centimeter. So let's see how that relates to d, which is the spacing between adjacent lines. Well, if you think about it, if I'm told the total number of lines per distance, if what I want is the distance between lines, it's basically just the inverse of that. In other words, d, if I've got 10 to the 4th lines per centimeter, d would be 1 over 10 to the 4th lines per centimeter. Because you'll notice that what that gives me is 1 times 10 to the negative 4th centimeters per line. In other words, that's the spacing between the openings. Now, remember, when we use D in the interference formula or the diffraction grating formula, we always want it to be in meters. And so D would be 1 times 10 to the negative 6th meters. And we can just drop the line at that point because, in other words, that's the space in between between adjacent lines, and that's what D is. Why don't you go ahead and try out this problem? You might pause the video. It says a diffraction grating contains 10 to the 4th lines per centimeter. What is the angle to the first order maximum for light with a wavelength of 450 nanometers? Okay, so we've already figured out that D is 1 over 10 to the 4th lines per centimeter, and that was 10 to the negative 4th centimeters per line, or 1 times 10 to the negative 6th meters is going to be our value for D. And now what we want to do is just take the formula. Remember, it's the same as the double slit interference formula, nothing different about it. And we want to solve that for theta. So theta is going to be the inverse sine of m lambda over d. Now we want the first order maximum, so that means m is equal to 1. So I've got the inverse sine of 1 times the wavelength, 450 times 10 to the negative 9th meters. Again, got to make sure I got everything in meters, divided by 1 times 10 to the negative 6th. And if you calculate that, what you should find is that theta is equal to 26.7 degrees. Now, there are a couple important things to say about that. First of all, notice not a small angle. And that's because we don't want it to be a small angle. If we're trying to measure different wavelengths, we want those wavelengths spread out as much as possible. And that's why we use a diffraction grating, because the lines are so close together, the pattern, the angles will be much bigger, and that means we can make more accurate measurements. So that's exactly what we want, but the only thing to remember about this is don't use the small angle approximation when you're dealing with a diffraction grating, because it won't be right. Let's talk about the line spectra of atoms. This is ultimately what allows us to be able to figure out what the universe is made of. So it turns out if you take any element and you heat it up in the form of a gas, what you'll find is that element will give off a unique pattern of light colors. And where this comes from is it comes from electron transitions within the energy levels of the atoms. So at some point in high school chemistry, you probably learned about that electrons can be in different orbits. And when an electron makes a transition from a higher energy level down to a lower energy level, it has to give off that energy, and it gives it off in the form of light. And it turns out that the light that's given off is tied to the energy difference between those levels, and a specific energy difference between levels will correspond to a specific color that's emitted. And so the energy levels of atoms is quite complicated, but what we find is that each element will have a distinct pattern of colors that it emits when heated in the way that I've discussed. So for hydrogen, if we take hydrogen gas and we heat it up inside what's called a hydrogen discharge tube, the light that comes off will only contain these specific colors. And that's true for the other elements as well. Now, this is well documented here in labs on Earth, and so we know what the patterns are for all of these elements. So now we take our spectrometer, we connect it to a telescope, and we aim it at some distant object. we take the light and we put it through the spectrometer and we measure what lines are present in that distant object. And by doing that and comparing it with these known patterns, we can actually identify the elements that are in that distant object. So it's pretty cool. This is really the way that we know what the universe is made of. It's also the way, by the way, that we know that the universe is expanding. You may have heard of the fact that light coming from distant objects is redshifted. And what that means is that it's shifted towards the red part of the spectrum. So for example, if we look at a distant star, what we'll see is that the hydrogen lines, the pattern is still the same, but all the lines have been shifted towards the red side of the spectrum. And by measuring that shift, we can actually determine how fast that distant object is moving relative to us. So that's how we know that the universe is expanding. So there's a lot of important applications to this in astronomy. So let's do one last review question to finish off our discussion of interference and diffraction. So the question is the pattern below due to a single slit or a double slit? So what do you think? Well, hopefully you realized that it's a double slit. And the reason that we can tell it's a double slit is because we're seeing both interference and diffraction simultaneously. And that's what we always see with two or more slits. Single slit, just diffraction. Two or more slits, diffraction and interference. Let's see if you can get the next part of the question. Which part of the pattern below is determined by the slit separation D, and which part is determined by the slit width A? What do you think? Well, hopefully you know that the little dots, and I'm not going to draw an arrow to all of them. So in other words, all those, all those, all those, and if you can see them, those as well. That is all due to the slit separation, right? Those are the little interference dots. So that spacing is controlled by how close or far apart the two slits are from each other. These bigger dark gaps, that's due to the diffraction pattern. The diffraction pattern is determined by how wide each of the slits are. Okay, so the overall diffraction pattern is controlled by the slit width. The little dots, the interference pattern, is controlled by the slit separation. Just to emphasize that a little bit more, remember that if I had a single slit with the same width as each of the double slits up here, what I would get is I would get a broad central maximum, right, corresponding to that area right there. And then I would get much less bright areas here and here, and even here and here, corresponding to that, and that, and that, and that. So if it were just a single slit, we would have just had a nice broad red blur here, and here, 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 and here. But because it's a double slit, within that diffraction pattern, we get the little dots of the interference pattern. Okay, that's the end of this video that finishes our study of interference and diffraction.